This is my Lab 5 motion of a shooting basketball. In this lab, I will introduce the key equations and key objectives in this lab. I will then play my video within Tracker, show the data I collected, display my glow script codes with drag and no drag, show my graphs comparing all the models computed within this lab, and finally close with discussion and conclusion. The purpose of this lab is to observe the motion of a shooting basketball into a hoop and account for the forces acting upon it, such as drag and gravity. From there, I will construct a model accounting for all the forces acting upon the ball. Some key equations that will be used are Newton's second law, which force equals mass times acceleration, being divided into F net divided by mass, and finally written as the final velocity equals initial velocity plus the net force divided by the mass times change in time. When an object falls to the ground, the velocity of the object is not constant. Since the velocity is not constant, we know there's an attractive force between any two objects with mass, so we can calculate this using the gravitational constant G, which in this equation is 9.8. Drag force is a constant that is opposite to any object in motion. This can be calculated by using the equation b times velocity squared, where b is a proportional constant that depends on the properties of the object. This is the video of me shooting a basketball that I placed in Tracker. First, I set the origin of the center of the ball. When the video plays, you can see where I track the points in the trajectory of the ball. From the Tracker video, I was able to extract key data and information, such as the initial position and initial velocity, which will help me in constructing the computational model. On this page, I just have documented the ball's mass, its radius, the start time of me shooting, the end time when the ball hits the goal, the time step of each frame, the initial position, the B constant, and net force, which I will later talk about within this video. Before we input our key data, first I construct two graphs, one for the X direction and another for the Y direction, seen in lines 9 through 12. The reason for these two graphs is to find and identify the Y graph and use that to compare to the observed model, as we only care about gravity and what goes on in that direction. Next, we input the ball's mass, the ball's initial position, and velocity, which we extracted from Tracker. Next, I set delta T to 0.033 as we was given that from Tracker. Next, I set G equal to 9.8, as this is important because acceleration equals gravity in this example, because as stated before, I am only accounting for gravity taking place. After that, I set the while loop so the model can compute for every time frame until it reaches the end, being 1.2 seconds. From there, I set Fg equal to 0, negative b ball dot m times g, 0. What's important is that because there is a 0 value for the x direction, no matter what happens, there will be no acceleration or deceleration, as I'm only accounting for gravity, which happens in the y direction. F net then becomes equal to Fg, as I assume there is no air drag and the only force acting upon the ball is gravity. Finally, I update the velocity and position formula and run the code. In the second glow script code, pictured to the right, everything mostly stays the same from the previous code, except now I've taken into account drag acting upon the ball. Here in line 25, I've added drag force equaling to 0.019 times the magnitude of the ball's velocity times the ball's velocity. In this statement, 0.019 is B. Next, I updated the net force to be F grav plus F drag, as I'm now accounting for both drag and gravity within this lab. Here's a graph based off the observed model and the computational model without drag. To the left, the red line is the observed and the blue is the no drag. As seen, both models mimic each other but begin to differentiate. This differentiation insinuates that there is another force acting upon the basketball. The graph to the right displays all three models, the red again being the observed, the blue computational model without drag, and the gray being the computational model with drag being accounted for. As seen, the drag computational model favors the observed model a lot more than the one with no drag. However, it also begins to split away, and this can be due to errors I have caused within the Tracker software, as this is explained more so in the next slide. The discussion question asks, how much energy does the ball have? For this question, we set the ball as the system and analyze the ball at rest, being at 0 meters per second, to when the ball is released from my hand, which is 3.6 meters per second. The change in height during the time interval is 2.6 meters. To figure out the energy, I start from the energy equation delta E equals W. From there, I can expand the formula where kinetic energy is equal to a work due to gravity plus my hand. I then isolate the work of my hand and fill in the known equations to find the work done by my hand, which becomes equal to 2.203 joules, meaning one throw of the basketball is equal to 2.203 joules as well. As seen in my graphs, there are errors and discrepancies. These can be caused by me not properly calculating the proper release of the ball, as well as not accurately tracking the center of mass of the ball within the tracker software. With better accuracy, the predictive model will closely model the computational model. In conclusion, I can say that Newton's second law and drag force played a crucial role in this lab. This lab shows the importance of accounting for all forces when attempting to determine the net force.